We going? Oh, okay. We're recording now. Fantastic. A nice exchange at the end. All right, we'll get started. I think it's actually a minute early, but we have a few announcements to start off with before we get started. All right, well, welcome back, everyone. Hope everyone had a nice spring break. I guess they're never quite as relaxing as you hope, and everyone's, so I'm sure, primed to take a midterm next week. Just really in the mood for it. All right, a few announcements before I forget these things, though. First of all, many of you, though not all of you, I believe, should have gotten feedback. I know not all of you should have gotten feedback on your proposal. If you haven't yet, we're hoping it's done by break, but if you haven't yet, it'll be out by the end of today. So I'll submit it tonight. You will get that on Piazza if you have not gotten it yet, and I think about half people haven't gotten it yet. So just still reading them, but it should be out soon. They're very short. They're like a sentence long. Either looks good or think about improving this, but hopefully it'll get you on the right track. I think because of a little bit of the pushback of the original project deadline or proposal deadline, and then also little delays here, we'll push back the milestone by a week or so, but the final will still be where it is because the final is the final. There's also a question on Piazza, and I want to address it in class, about the student presentations for these projects. There are student presentations. These are very short. We're doing them all in one day. They're about 2 minutes long. It's really just to highlight your work, the basic stuff you've been doing, and get people excited about the work, and maybe come to the poster when you're presenting it. So it's a showcase. It's not intended as that big a part of the evaluation, but it will be part of the project as a whole, and it'll count some small percentage of your final grade. I think it wasn't in the final rubric, so we'll make that up, what percentage it'll cost of your final grade, but it won't be very much for the project grade, that is. What else was there? Vittorio has some of the homeworks for homework 1 in the back there. If you did not get that, you can go get it from him at the end of class. Don't do it right now. And then there was one more thing I wanted to mention, but not remembering it right now. So we'll also submit, well, the midterm, it's next Monday, and it'll be in class. It'll be fairly short. It's short answer, multiple choice. So don't worry too much about it. It'll be covering the material we have so far, but really it's just kind of a review. We're not going to make it open book, not because we don't want to, just because there isn't enough room in this room to have open book tests. Everyone will be sort of messing around, hitting each other with their books. So we'll make it so that you should be able to answer all the questions without a book. So we'll make it of that level. I think that was everything, though. Are there any questions now that everyone's back from break about really anything? Homework 2 should be back in a week or so. And someone also mentioned the midterm grade. We'll try to get back as soon as we can so that you will know your grade by the add drop deadline, to either change your grading or to drop the class. No one should hopefully drop the class because of the midterm, but you could make that decision, I guess. All right, were there any questions before we start? Yeah. Yeah, there's a presentation for the poster, which is also part of it as well. That's in lieu of a final exam. During the final exam time, we'll have poster presentations, and that will be going. I realized that the description didn't include all that, though we have it in the syllabus, I believe. So yes, those two are both components, but as we get closer to that deadline, we'll start talking more about that. Yeah. The midterm has no programming, no. You can't do any real programming in that amount of time. Programming is for the home. We give you plenty of programming for the homework, I feel like. You could have a little break from that for a midterm. All right, anyone else? Okay. Well, something else. Let's get started on probabilistic inference. So this was actually meant to be shortly after, originally, the last lecture on probabilistic modeling, but split up a little bit. So I do have a little bit of a refresher here on some concepts, but this lecture takes a little bit broader view of graphical models as a whole, and then how we actually answer probabilistic questions in these graphical models, which is really the inference question. Let's just dive right in. The lecture today is going to be really about 3 different things, and it's mainly these first 2, and I'll talk a little bit at the end about approximate inference. But first we'll talk about probabilistic graphical models. So you've already seen this to a certain extent, because last lecture you heard about Bayesian networks. This is one of the main examples that we're going to consider of probabilistic graphical models. But I'll mention some others as well. And in fact, the main one I'll talk about through the rest of the class is a representation called factor graphs. Factor graphs actually generalize Bayesian networks and a bunch of other models, and they're really kind of a nice form to actually manipulate these things and do operations on. So we'll talk about factor graphs and also Markov random fields in the first thing. Then I'll talk about exact inference. And exact inference, I'll both define what I mean by that. So you might have heard the term inference before, but I'll formally define what I mean by inference. And there are different types of inference. There's things like marginal inference, which just says what's the probability of some subset of the variables in your model. There's things like map inference, which says find the most likely assignment to variables and things like this. But I'll define what I mean by those, and then we'll go through some cases. And we'll particularly cover the variable elimination algorithm in some detail, so you actually see how to actually perform inference in fairly complex models. And finally, I'll end by talking about two forms of approximate inference. One of these is going to be sampling-based, called Gibbs sampling. It's a very simple method, which is actually used hugely in practice. And I'll also talk a little bit about inference as optimization. How can you solve inference problems using techniques from optimization? This has really been kind of a big trend in research in the past, say, 15 years or so. Well, let's just jump right into probabilistic graphical models. So we saw some last time, but taking a little bit of a step back, I want to kind of remind everyone that at their base, probabilistic graphical models, as we're going to talk about them, are really all about representing distributions over random variables. We want to represent P of x. And for this class, this lecture at least, x is going to be binary valued. So each element in x, or rather, each element of x is binary valued. Right? So each element of x is a big vector of binary random variables, and P of x is a distribution over those random variables. Okay, now the extension to multivariate random variables is not that hard here. Much like classification, we started off with binary, and it's actually not that hard to extend it. Real valued random variables are a different beast to a certain extent, and you need different techniques, or you can just discretize them and treat them as sort of variables with multiple different values that are all discretized. But we're here going to focus for simplicity on just discrete binary random variables. Now, since we're talking about a vector, or x here, I guess, is a vector, then in 1, 0, or 1, and there's n elements to it. So these are n-dimensional binary random vectors. And naively then, if we want a distribution over these things, we just need to define the 2 to the n, possible assignments to x, and then their corresponding probability. Right? That's a complete description of these distributions. And we can do that actually with 2n minus 1 numbers, because the last number has to be such that they all sum to 1. Right? That's really all there is to graphical models, or discrete graphical models. But of course, this becomes very intractable quickly for large n. You can't just have big tables that grow like 2 to the n. That would not scale to, say, thousands of dimensional vectors here. And so probabilistic graphical models are a way of representing high-dimensional distributions like this using compact representations. That's really what they are. That's all they are, and to a certain extent. And they do so by exploiting what's called conditional independence. So there's certain independencies of these things. If there was no independence here, we would just need to write all the 2 to the n values. But because there are certain independencies, we can actually represent these more compactly. Now, a quick bit of notation before. I actually don't have this in the slides, but I was just thinking about this. Quick bit of notation here. We are going to refer oftentimes to things like this, P of x, or P maybe of xi, which means some sort of smaller subset of that. It's important to know what this refers to. So usually when we write this, we mean actually the vector of probabilities that this corresponds to. So this is a function, but you should think of it like a vector. Okay? Just think of it like a vector that has all its values in it. And that goes, by the way, for other functions too. When we write things like f being some factor, say, of xi, you should just think of f as being a number for f of xi being equal to 0, a number for xi being equal to 0, and a number for xi being equal to 1. Now, there also is some ambiguity here, though, unfortunately, because we also write things like this. We also write things like the sum over xj, p xi xj. Here, xj is actually an instantiation of a variable. right? So this whole thing is essentially a distribution over xi, and we are summing over xj. So whether or not one of the arguments denotes kind of an arbitrary input, which means that your thing is actually kind of a table of values, or whether it means a particular input is somewhat arbitrary, unfortunately. You have to figure it out from the usage. Now, the book, I think, gets around this a little bit by trying to say big letters are the variables, the generic ones, and little letters are assignments. But this is not standard, and part of this graduate class is to kind of prepare you to read papers in the field. You will not see that everywhere. You will see stuff like this. So you have to get used to the fact that think of how to think of these things either as vectors of just numbers or as instantiations given a particular assignment to these things. Sometimes I will write things like this when I want to sort of be very clear that I mean an instantiation of this, but I won't always do it. Sometimes notation is just a lot easier to write if you don't write it like that. So apologies for that. It is unfortunately just sort of the notation of the field. And actually, if you just sort of understand that and know, then it'll be a lot easier to read these kind of things. All right, so let's jump in. A Bayesian network. We talked about Bayesian nets last time, and so this is going to be kind of brief. But essentially, a Bayesian network is defined by two things, right? It's defined by, first of all, a directed acyclic graph, where the nodes correspond, the vertices correspond to the random variables, and it has a bunch of edges. And it also has a set of conditional probability tables that define the probability of xi given the parents of xi, where the parents of xi mean the parents of xi according to this edge structure of this graph here. I'll give an example in a second, but you're hopefully all pretty familiar with these things. We saw them last time. Now, these define the joint probability distribution of p of x equals the product of all these different conditional probability tables here. From I equals 1 to n, p of xi given its parents. And the parents could be null, by the way. They could have a node with no parents, too. That's fine. Now, another way of stating this, and the fact that these two things are equivalent is not obvious. One way is pretty easy to go. The other way is very hard. Or not very hard, but it's harder. Is to say, another way of saying this is to say that in a Bayesian network, each node is conditionally independent of all of its non-descendants. So of anything that is not a descendant of that node, given its parents. Now, proving the equivalence here is actually kind of tough. We're not going to do that, but I'm going to give an example and kind of go through what this sort of means, because you should have some intuition of this, even if sort of proving this rigorously is a little bit beyond the scope of this class here. So we're going to take one of our favorite BayesNet examples here. This is in the book. I don't think we mentioned it last time, but maybe this was one of the examples last time too. Maybe it was. But basically, there are a bunch of random variables. Here, it's 5 random variables here that say, is there a burglary? Is there an earthquake? Is there an alarm in your house going off? And if the alarm's going off, does your friend John call or does your friend Mary call? And the way to define this probability distribution here is to give this graph. This graph says, for example, alarm is going to be defined as a function of its two parents. And then to give this graph and then give a set of these probability tables that describe the probabilities involved. Okay? We saw this all last time, so this is all review here. So x1 has some probability of being 1. X2 has some probability of being 1. This is a probability of being 1 given different assignments for its parents. Note, I'm not writing the probability that it equals 0 here. That would just be 1 minus this number here. And then similarly, if there's an alarm, if there is an alarm, then John calls you with probability 0.9, and he doesn't call you with, or if there's no alarm, he calls you with probability 0.05. Okay, so this is sort of the basic thing you've seen before, right? And the thing to sort of keep in mind here is how this structure here, first of all, reduces the size of the distribution you need. There are 5 random variables here, so you need 2 to the 5 minus 1 parameters to describe that distribution if you just were to enumerate every single possibility. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters, which is much lower. So we've represented this more compactly. The other thing is to get some intuition about how this graph structure lets us decompose the probabilities here. So we can use this graph structure to write out the probability over all x. That was a distribution, right? And the way I'll do this, and it's worth sort of going through this once, and this kind of codifies, I think, the conditional independence assumptions as well. After this, I'll be done with Bayes nets, because we saw it again before. But essentially, you can write p of x, p of all the variables, as just by definition, this is just the chain rule. So this holds true for any probability distribution. P of x1, then p of x2 given x1, p x3 given x1 and x2, etc. P of x4 given 1, 2, 3, and p of x5 given 1, 2, 3, 4. This is just a general rule. It's called the chain rule of probability. It holds true for any distribution. It is not specific to this. It's really just the definition of conditional probabilities, actually. And the nice thing now is this Bayes net structure lets us say, well, these probabilities here can be simplified. Because in this case, for example, x4 given x1, x2, and x3, this is conditionally independent of everything else given its parents. In this case, its parent is just x3. So this term here, p of x4 given all these things, simplifies just to p of x4 given x3. Okay, and that's the structure of Bayesian network that you should sort of always have in mind. And that's why this is sort of, at least intuitively, one direction of the equivalence between saying things are independent of their non-sentence given their parents. That implies that it actually factors according to these sort of product of different conditional probability tables here. Yeah?
Why is there x4 in the last term?
This one. So for the chain rule, I'm just writing the definition here. So when you're at the chain rule, essentially it's boiling down to the fact that p, right, x1 given x2, that's just by definition, right, equal to p of x1 and x2 given p of x2. Okay, so in other words, you can multiply this over here. That is just the definition of really conditional probability. Has everything that is not, everything before x5 has to come in the given. Now, the simplification we make is to say, well, p of x5 is independent of everything else given x3. So we're not going to write all this. We're just going to write this term here. Because this term here is equal to this term given the independencies defined by the Bayesian network. It is before x5, just in the order of variables. So this is just a rule of probability, right? Is that essentially it's this thing. I mean, this is the rule here. P of x equals p of x1 times p of x2 given x1. This is independent of anything here. This holds for any probability distribution. Don't worry about this. This structure lets you simplify it to get rid of that. Right, so that's important. All right, that's it for Bayes nets. Let's talk about Markov random fields. Who here has seen Markov random fields before, by the way, actually, just by a show of hands? Okay, not that many, actually. Okay, great. So a Markov random field is essentially another kind of probability distribution that we can define that also can capture high-dimensional distributions while maintaining a compact representation. Okay, and there's a different form now. This is now a different representation. It's not the same as a Bayesian network. It is now represented by an undirected graph, G, where vertices correspond again to the random variables, and there are some edges. And here, there are two sets of functions here. They're what I'm calling a set of unary potentials, which for every variable, there's some potential associated with that random variable. Which basically, you can think of these potentials kind of like probabilities, but not normalized. We'll give an example in a second. And then there are a set of binary potentials that encode potentials between two different nodes when there is an edge in the network between those two nodes. Okay? And the definition of a Markov random field is just that p of x equals 1 over z. Now, z here is an important term, but really it's just a constant. It's a normalizing constant. because these things don't actually have to be probability distributions, we need to actually normalize it at the end. These could just be arbitrary. They actually have to be positive, but they can be arbitrary functions. And our distribution is just defined by this term here. So P of x is just equal to some normalizing term times the product of all the unary potentials times the product of all the binary potentials. Okay? You can define Markov random fields over more than just binary potentials, but typically you just aim for binary. You can actually reduce any higher order thing to a binary case with just expanding some variables. So you'll typically see them in terms of these binary variables here. Or sorry, not binary variables, binary potentials. Now z here is just the term that makes this thing be a probability distribution. Namely, the sum over all of these things has to equal 1, right? We know that from probability distributions. They have to equal 1. I guess I don't say it here, but these are all positive, too. So these always output positive numbers that we'll consider. You can have negative ones, but that gets really kind of nasty. These are all positive here. And so z is just going to be a sum of all these terms for every single assignment of x. So again, think of your notation here. This here means that x is sort of some arbitrary input, right? So this whole thing you should think of as a big vector of 2 to the n, this whole term here. This term now is a scalar. So what I'm doing is I'm taking all the x's, I'm summing over all those x's, computing this term, and adding them all together. And then dividing by that, and that's what I do to normalize the distribution and make it so that the probability here is actually a probability distribution. But that's a Markov random field. Okay, now just like a Bayesian network has kind of two interpretations, right? A Bayesian network, you could either say, oh, it's either this scenario where you just define the probabilities in this way. It's the product of all the xi's given their parents. Or you can define it in terms of conditional independence. Markov random fields are the same way. So it's actually the case you can say that this definition here is equivalent to the fact that for any xi, p of xi given everything else, I'll write that as p of negative xi, this is equal to p of xi given just the neighbors of xi. I'll write it like this for now, even though I'm writing out neighbors there fully. Don't want to write too much on the board. And this is, by the way, not at all obvious. This is the case. You'll have to just trust me on this one. And I'll give an example in a second, though. Actually, that example isn't going to be great because it's just two nodes. But essentially what it says is if we have x1, x2, and x3, and this is our graph structure, it means that x1, if we have a distribution like this, that means that x1 given x2 and x3 is equal to x1 given x2. Not at all obvious, by the way. This is not, and it's not even easy to show. I mean, this is several lines, several pages of a proof to show this. But it is true. So I'll have to just sort of take my word for it here and kind of get familiar, if not with the actual proof there, with just these two different potential interpretations. Meaning that we can either define it just in terms of the probabilities here, or in terms of these conditional independencies. In a second, we'll see a general structure that I think will hopefully clarify some of these things, that sort of makes these things a little bit more obvious. But this is the definition here and sort of properties of a Markov random field. Let's look at an example, though. Hopefully this will clear it up a little bit. Here, actually maybe not, because we don't really have much conditional independence here, but I'll still give this example here of just two nodes. Here we have two nodes, and there's no sort of alarm earthquake example here. It's just two nodes, two variables. We're all abstract at this point, right? We can think in terms of just the raw math. So what we define, we have these two variables, and we have an edge between them. What that means is we want to define potentials for each of these things. Okay, and potentials, again, just like probabilities, you should think of as tables. They are essentially a table that gives some value for all their possible inputs. So here we have a potential for x1, and that says the potential for x1 being 0 is 1, and x1 being 1 is 5. Those are arbitrary units, by the way. They're just numbers. They don't become probabilities until you get to the very end and normalize everything. Okay? But you can kind of think of them like kind of inclinations towards probabilities. So that this potential here, for example, would say x1 kind of by itself, ignoring everything else, it kind of wants to have value 1 with some sort of strength 5, and it has value 0 with a strength 1. Okay, that's very unrigorous there. That's kind of how you can think of these potentials. Similarly, there's a potential for x2, and in this case, those are just the opposite ones there. I'm just flipping it around. So x2 kind of wants to be 0 in some sense, and wants less to be 1. And then there's also a potential jointly over these two things. Again, none of these are normalized here. These are just kind of independent functions that kind of give the propensity to be like one thing or the other. And here, the potential on 0, 0 is 10. Potential on 1, 1 is 10. And probably shouldn't pick this. Looks like it could be binary there, but this is actually 10. This is 1. And 1, 0 is 1, and 0, 1 is 1. So what this says is that this potential encodes the propensity for these two variables to take on the same value. Right? Because this is a strength of 10 being the same value, and a strength of 1 being different values. Now, the way to actually get a probability here is to go through the process of actually multiplying these things all together. So, for example, we can actually, remember, our probability here is equal to the product of the univariate potentials times the binary potentials. And so we can just multiply them together. So if we have x1 being equal to 0 times x2 being equal to 0, that, for example, would be this potential here times this potential here times that one there, which would be 50. Similarly, this one being 0 and that one being 1 would be this guy here times this guy here times this. Oh, that's actually wrong. That should be 1 there. Oops, messed up my math. Anyway, is that right? Yeah. Oh, well. OK, so these numbers are wrong. Ignore that number there. I'll fix them in the slides later. But essentially, you see, this is a great thing about giving lectures for the first time. Essentially, what you do, if you do it correctly, is multiply these together. So you would have 0 times 1 times 1. So this would be actually 1 here. Sorry, 1 times 1 times 1. So this would be 1 here. This would be 5 times 1 times 5. That would be 25 here. And this would be 50 again. And actually, this would not then sum to 150, but there was something else, and you have some other random fractions there that you would get if you checked this more diligently than I did. But does that make sense to everyone, at least? How do you go about constructing these things? Ignoring this 50 here. You just take the different assignments, you multiply the potentials together, and then at the very end, you divide by the sum of all those different potentials to get the actual normalized probability distribution. All right, moving right along. Let's talk about one more type of probabilistic graphical model, which actually generalizes all these things, those two. And it's very nice, because I actually think that Markov random fields kind of actually confused me the first time I saw them, because sometimes you can define factors over more than just two things, and when can you do that? And it's sort of really kind of confusing. Similarly, it sort of can be hard sometimes to see a Bayesian network and say, okay, really what's related? This thing of non-descendants and ancestors and all this kind of stuff is kind of confusing. Factor graphs give a very nice, in my opinion, kind of clean framework for all of this. They also actually can represent things like constraint satisfaction problems very nicely. So actually, even independent of probability, they can be very nice for their own, for other reasons. But they're very nice for probabilistic distributions as well. So, last thing we'll talk about today, and I'll give some examples, and our last type of model we'll talk about today, is a factor graph. So a factor graph is also a graphical model, like we expect. But here, nodes can actually be of one of two types. So we're actually going to let nodes or vertices in the graph correspond either to a variable or to a potential. So like the Markov random fields, we could think about potentials here, but the actual vertices correspond to potentials. The edges in the graph are only between variables and potentials. There's never an edge between two variables or an edge between two potentials. Always between one potential and one variable. And essentially they correspond to, there's an edge between factor fi and variable xj if and only if this factor includes that variable. So this will hopefully become much more clear when I talk about how we can represent base nets or MRFs through this. But hopefully this makes some sense, right? Basically, there's a bunch of factors, a bunch of variables. The graph says how they correspond to each other. What's sort of the scope of variables that are the input to each different factor. Similarly, we can define the joint distribution here. P of x is just equal to, and I like them partially because the form here is so simple. It's 1 over z again. We have the normalizing constant because they're not necessarily normalized, times all the factors, so I equals 1 to m, of fi, and then script x I, where script xi just means all the variables that have an edge to that factor. We'll see an example in a second. So hopefully that makes sense, at least being simple to write down. Let's see what this actually looks like. So let's first of all talk about how you can convert an MRF to a factor graph. It's actually, this one's really simple because it's almost immediate. Here is our Markov random field. We know we have the two potentials there. Three potentials. One for this guy, and one for their joint potential. And the factor graph, as you would expect, is just this, right? So instead of just having the edge between these two variables, you throw the actual factors into the graph itself. And connect this one to this factor, this one to that factor, this one to this factor, this one to that one. And it's much more obvious to me, at least when I look at this, the structure of the graphical model when I see this. I can say, OK, f3, those variables there for f3, for example, that's the factor that involves x1 and x2. f1, that's the factor that involves x1. f2, that involves x2. So when I look at these, it's very easy for me to tell sort of what's going on by this. And it also should be hopefully pretty clear that this is exactly then the same form as the MRF, right? Because the MRF had one potential here, and one here. You just multiply those all together. And here we're just doing that same thing. We're multiplying all the factors together. It would be f1, which would just have x1 here, f2, which would just have x2, and then f3, which would have x1 and x2. It's a little bit less obvious, initially at least, how you would convert a Bayesian network to a factor graph. But it actually isn't that hard at all. It's exactly this as you might expect. So basically, you take all the things. So basically, you have one term, for example, that says how x3 depends on x1 and x2. And whereas in a Bayesian network, that is defined by looking at the parents, which ones are parents, which one's the child node. In a factor graph, you would just remove all the directions to those edges here and just have a factor that represented the interaction between x1, x2, and x3. So whereas before, for example, we had this probability, the probability of x3 given x1 and x2, that just converts to some factor. And here it's x3, which is a function of x1, x2, and x3. So for example, if we take this bottom right node here, saying the probability that x5 equals 1 given x3, that is the conditional probability of these two variables defined by the Bayesian network. In a factor graph, that would be the exact same thing. You just typically enumerate all the possible combinations here. So even though these sum to 1 in a Bayes net, we know we can kind of not use all the parameters here. In a factor graph, you usually represent all the parameters. And that's the only difference. You have your 9.9 and your 0.01 and your 0.3 and your 0.7. So to sum up this part here, factor graphs, essentially, they are a nice generalization of this thing, of both models like Bayesian networks and Markov random fields. And they allow for us to kind of define processes like inference in a kind of a more general way. We don't have to worry about one type of inference for Bayesian networks and one type for Markov random fields. We can just write inference once and be done with it. Now, of course, there are specialties to a Bayesian network. For example, in a Bayesian network, these factors have certain properties. Namely, these two will sum to 1, these two will sum to 1, etc. But we're not going to exploit that, at least here. We're going to define general inference procedures which can work for any factor graph, be that a Bayesian network, a Markov random field, etc. Which is very nice, because then we don't have to worry about kind of these more complex specifics to a Bayesian network or to a MRF, etc. All right. Are there any questions about any of this thing so far? We're going to quickly sort of start using these things, so it's good to have an idea about the structure of them up front. Yeah?
Where do you normalize this data? Like, what is the difference between Bayesian and MRF?
Well, so there's a big difference, really. For example, if we have these three variables here, in a Bayesian network, I won't even write what they are, that graph structure there. To represent that as a factor graph, and forget about MRS for a second, to represent that as a factor graph, you have to do this. You have to just put a single factor on all these things, because there is a function that depends on all of them. Now, with the original Bayesian network structure, and an MRF would have to be the same thing, by the way, have to have an edge here, an edge here, an edge there. Now, with a Bayesian network, when you see this structure, you can still extract some conditional independencies from that. So you know, for example, that these two things are marginally independent, right? With this, you don't know that anymore. That's not encoded anymore by the graphical structure. It could be true given whatever values there are in the tables, by the way, and it will be if you're directly going from a Bayesian network to this. But the independencies that you're encoding are lost in this. Similarly, if you have an MRF that's like this, I won't really go into details here, but this is very hard to encode these exact same, in fact, you can't encode these exact same conditional independencies with a Bayesian network. So the reality is, a factor graph generalizes these things, meaning anything you represent like this can be represented in one of these two forms, or anything in one of those two forms can be represented as a factor graph, but you lose some of the inherent sort of read-off ability of seeing where independencies are from the graph structure itself. And so because of this, people still do use MRFs and Bayesian networks, even though for our purposes, we're going to say, look, it's fine if you give us a problem in that definition, they'll think about it with those independencies, but we're going to convert it to these factor graphs to actually run our inference procedures. But they are different, and they encode different probabilistic assumptions, these two different models. Anything else? All right, let's keep moving along. Let's talk now about exact inference. So first of all, what do I mean by inference? Inference in general is sort of the name for a bunch of different questions we can ask a probabilistic model that we may want to ask of one of these models. Okay? So, for example, there are several types that we actually might want to ask. One kind of common thing to ask would be, what's the probability of some xi? So if we have some distribution which gives us a probability distribution over p of x, and we ask the question, what is the probability of xi? x sub I, meaning some subset of the variables. And I can either mean here, by the way, I can either mean give me an actual table that describes this, or I can mean for some specific instantiation, xi0, say, what is that one number? Of course, the former would give you the latter, right? If you have the tables for all of them, you can just look up which one it is. But this is one question we might want to ask. And by the way, this is not an easy question, even if this equals all the variables. For a Bayesian network, it's pretty easy, because you just plug in the numbers into the tables. But for a Markov random field or a factor graph, you have that 1 over z term. And that term can be hard to know beforehand, unless you compute every single entry here. Right? So how can you compute sort of quickly, get the number for one single probability of a certain set of variables without computing the probability over all of them? That might be useful, right? Conditional inference. This is sort of a similar situation here. Now, we condition on some evidence, using the set E here for being the evidence set. We say, maybe I've observed some of these variables. We know they take on certain values. As we kind of mentioned this last time, we talked about knowing certain effect variables. If we know the value of certain variables in our vector here, can we compute the probability of other ones taking on certain values? Or in fact, can we compute a whole entire vector of what all the other values are given assignments to the known ones? Again, these are some subset of all the variables. They could be complete, so that the union could be actually all of them. They don't have to be, though. It could be a disjoint, or there could be things you still marginalize over in addition to conditioning on. And finally, there's another kind of type of inference here called map inference, for maximum a posteriori. Sometimes people call this most probable explanation, and some people actually kind of argue about why you should use one term versus the other term. I'm just going to use map here and ignore all those arguments. Map is fairly common in literature, and I'm going to call it map inference. This asks the question, given some distribution like this, can I find the assignment to the x's that is most likely, that has the highest probability there? Right? So can I maximize over xi? xi. And there could also be conditional versions of this. So maybe you've seen some, and you want to maximize this. xe equals xe0. So now that I've observed some, now what's the most likely assignment to my variables? Okay, so these are all things that are very useful to ask of a probabilistic model. For example, if we have our model of our earthquake, we might want to say, well, what's the probability that there's an earthquake given that John called me, or something like that, right? We'll go through a lot. We'll use this stuff in a lot of other examples as well. So for example, in computer vision, it's very common to represent vision tasks as Markov random fields, where each pixel in an image is a node, and you're doing some inference over, say, is the pixel a background pixel or not? Given what it looks like, what are the pixels? Are they background or not? That would be another example of an inference task. So these things come up very frequently. They're very useful to be able to solve. And so the question is, can we actually go about solving some of these? Can we go about answering these questions? The first thing I want to say is this is easy if we want to just enumerate all 2 to the n possible values of these things, right? So in some sense, our graphical models were themselves compact representations, but it's not immediately obvious how or if you can use that compact form to actually answer these questions compactly. So instead, let's just go ahead and ignore that structured form for our models. Instead, just enumerate every possible 2 to the n value. We say the probability of x1 equals 0, x2 equals 1, x3, this equals 0.05. You do this for every single possible assignment. And if you have that, you can answer all these questions. Right? Because if you want to know the probability of some subset of variables, you look at all your probabilities, take all the other ones. So x bar I here means all the other variables. And you sum out all those ones. It's just sort of a rule from probability, a basic rule. And by the way, for a factor graph, this would just be equal to taking the sum over all these things and summing over that. I guess I'm leaving out a 1 over, should be a 1 over z term here. But this is how it would look for a factor graph. And what you would be left with is just your probability of the variables you care about. Right, so the simple example would be, probability of x1, for example. You have a distribution over 2 variables, x1 and x2. You just enumerate all 4 categories. And the probability of x1 would be equal to the probability, the sum over all x2, the probability of x1 and x2. Simple, right? And it's the same thing for more of these things. Similarly, if we want to do conditional inference, it's no harder. This is the rule, this is the definition of conditional probabilities here. So we just take all our stuff that we know, we look at the probability of this and this, the variables we care about and the evidence, divide by the probability of the evidence, and that's our conditional probability right there. And these are both calculated this way, or just by plugging it in directly. Similarly, map inference is easy. We just look through our whole table and pick the biggest probability, and we're done. That's our map solution. You could also run conditional map inference, and essentially it's the same way. You just define this, and then pick the biggest one. So again, if we are willing to enumerate all possible things, we can answer all these questions. Of course, the question is, can we do it with less work than that? Can we actually somehow get away with doing less work than enumerating all of them by exploiting that same structure of the models that let us represent the distributions compactly? That's the question of inference. All right. So I think I said this, but the answer is yes, or I wouldn't be having any more of the lecture. When n gets large, you can't do that anymore, obviously. If you have 1,000 random variables, you cannot enumerate 2 to the 1,000. But you can sometimes, not always, not as easily as you would hope to, maybe. You can sometimes use the graph representation to derive a compact form of inference. And I'm going to do this in 2 ways. I'm first going to give you a simple example from a Bayesian network that hopefully kind of gives you an intuition about how this might work. And then I'm going to give you the general algorithm and go through it in some detail and see how that actually works. Let's start off talking about a chain graph here. This is a Bayesian network with 4 nodes, and defines the probability this way. So I'm just going to write it here. What we want to compute is we want to compute the probability of x4. Okay? That, again, this would be a vector with 2 entries. The probability of it being 1, the probability of it being 0. All right, so we know the probability of x4 equals the sum from x1, x2, and x3 of this probability, p x1, x2, x3, and x4. Right? That's just definition of marginal probabilities. Then we take the structure of the Bayesian network and we plug it in to simplify this. So for example, I'll go through this, but maybe I'll just write it out on the board too. So this will be equal to here, the sum of x1, x2, x3, probability of x1. That has no parents, so we're fine. Probability of x2, given everything before it. In that case, it's x1. The probability of x3, given x1 and x2, but by our structure here, the probability of this given all that equals the probability of it given that. So this is the probability of x3 given x2. And the probability then of x4 x4 given x3. Okay. So now what do we do? It seems like we have to sum over 8 possible values here, right? This is a sum over all possible assignments to these 3 variables, and there are 8 of them. Okay, that isn't very efficient. We're not really gaining anything yet if we just leave it in this form. The key sort of idea here, which you've probably seen before if you've ever done Bayes nets before, is that you can rearrange the products and the sums here, because not all these terms depend on all the variables. You can rearrange the products and the sums to make this computation more efficient. And that really is the core of what inference is. It's rearranging the order of operations to make things like big summations more efficient. So how can we do that here? Yeah?
Well, the last term, the last term is going to have 1.
Right.
The first term doesn't have this.
That's a better way of doing this one, yeah. Let's do it that way.
So you can change. You don't have to sum with the 3 over the last 2 terms.
Mm-hmm. Right. Does everyone get that? So here's the idea. These 2 terms don't have an these 2 terms do not have an x3 in it, for example. So we don't need to worry about the sum over x3 in those. And in fact, if we want to just look at the sum of x1, say, the only terms that have x1 are these 2. So let's write it like this. Let's write it like sum over x2 and x3 of these guys. These are the guys that have x2s or x3s in them. P of x3 given x2, P of x4 given x3. And take the sum over x1 and push it inside this multiplication here. So times the sum over x1, p x1 given x2, p of x2 given x1, p of x1. Okay, so this is just equivalent here. I'm just rearranging sums that don't depend on other sums. We can do that. And we can pull a constant outside of a sum, essentially. And for this purpose, these 2 are constants as respect to this sum. And now, we can just compute this. Okay? This is just a number. I mean, this is essentially, these are factors. This is a sum. We can go ahead and compute this one. And by the way, this is also, by the way, equal to this whole thing here. It's just going to be equal to p of x2. So we can compute p of x2, essentially. And from then on, these 2 things here really were distribution over 4. This essentially was a vector over 4 different variables. We sum out x1. Now we're left with just a 2-valued vector with 2 values in it. So I'll just go through that with the slides now. So we move the x1 here. We compute this sum. This is essentially a term over 2 variables. It has 4 entries. But we sum out x1, and we're left with a single term that has only 2 entries. Okay, everyone sort of get that basic idea? We can do it again. Now moving x2 here. This one does not depend on x2. Do this thing like that. And by the way, this term here, of course, is just x3. And now we're essentially done. I mean, I'm not going to write it, but you just sum over x3 again. And what you're left with is just, by definition, p of x4. Now that was many fewer operations. In the 3 cases, isn't that many fewer. But you can imagine if you did this sort of for a very, very long chain, you could do that for however long the chain was. Essentially have a number of operations that is linear in the size of the chain. Whereas summing them all over the beginning would be exponential in the size of the chain. And that is how probabilistic inference works. Taking shortcuts like that is what it does. So now I'm going to sort of bombard you with the full algorithm right now. But it really isn't very complicated. It's just exactly formalizing this process here. So the concept that we're going to talk about here, was there a question there?
Yeah. What if the network is not single chain rather than chain intersection?
Yeah.
So will it work?
So for tree, we're actually OK as well. What I'm going to show next is how you do this for general factor graphs, actually. How you eliminate a variable from a factor graph. And that will tell you exactly how to do it in all those cases. So the basic idea here is a method called variable elimination. And at its core is a way of taking a factor graph, so an input g being a factor graph, and some variable xi, and you generate a new factor graph g that has that variable removed. You've essentially, in this case, you've marginalized out that variable. You've summed over all possibilities of that variable and kind of taken the average factor graph for that, ignoring that variable, or looking just at the expectation over that variable. That's what variable elimination does. This is sort of essentially what we're doing here. So for example, this step here would have been eliminating x1 from this chain, because the next step here no longer has x1 in it. Similarly, this step here, computing this sum, would eliminate x2. And lastly, we would eliminate x3. This procedure here is just a way of eliminating a general variable from a factor graph. So now you can have all sorts of crazy structure you want. You can be as sort of complicated as you want. This will tell you how to eliminate factors. Or sorry, eliminate variables. So maybe I'll just draw a quick one. I have an example on the next slide too, but do it while I'm showing this. So you have some factor graph. I won't even bother labeling the variables. But say we want to eliminate this variable here. What we do is there's a few steps to this. We first identify all the factors that contain that variable. All right, so that's going to be the set F here. It's going to contain all the factors. So factors are vertices, remember. So all the factors where fj and xi is the variable we're eliminating, fj and xi is an edge. That, by definition, are all the factors that contain xi. Those are our factors. In this case, if we want to eliminate this guy here, that would just be both these two factors. Maybe I'll put another factor off the side here so we don't eliminate everything. So that would be these two factors in that case. That would be f. Then we look at this set x tilde. And x tilde is all the variables that belong to these factors. So we're doing this sort of one more time. We're sort of spreading out one more time in this graph. And we're looking at these variables here. And I'm not going to include xi in that. So I'm actually going to take out xi. So this x tilde would just be these guys. OK, so that's sort of just definitional. The notation's here kind of complex, but hopefully it kind of makes sense too. It's basically saying this is all the factors such that this factor and that variable are in the graph. This is all the variables such that there's some factor that variable and that factor are also in the graph. And then we take out this variable, xi. This step here is really the most important one. This is why it's called the sum product elimination, because you take a sum and a product here. So this is the important step. What we do here is we take all the factors in f, and we multiply them together to form a bigger factor. So in this case, I'll just name these. Call this f1, f2, f3. This is x1, x2, and x3. OK. Now, we take all the factors, we multiply them together. So essentially, f1 is a factor that involves x1 and x2. F3 is a factor that involves x2 and x3. OK? we form a new factor by their multiplication. So the new factor we have is just going to be a factor x1. Well, I don't even name it here. It's just the product of these things. X2, let's see, f1 and f3, x2, x3. I have another example in a second that's just not going to be on the board here, but hopefully you can read kind of my scribbling here. So that's this product. So that's the product here, this part right here. Right? Remember, script xj is just all the variables that belong to that factor. So in this case, this would be 1, 2 for this one, and 2, 3 for that one. OK, so now we have a factor that depends on both all the variables in x tilde and xi. Because by definition, these factors had to involve all the variables in x tilde plus xi. So this factor here is really again, think of it as a big table that has a value for each possible combination of xi and all the variables in x tilde. Then, and that, importantly, is that is everything in the network that has anything to do with xi. Right? Because if there was a term that involved xi in our network, it would have to be in one of these two factors. So everything else, which in this case is nothing, but which will be something in the examples I'm showing you, everything else doesn't have to do with xi. So we can eliminate xi from the entire network by looking just at this product of factors there and summing out, in this case, over x2. We're eliminating. What we get is a new factor, which is over these variables x tilde. And all we do now is we just add this new factor to our network. So we take out xi and all the factors in f here. We take those out. Those are no longer vertices. We add this new vertex f tilde. Remember, vertices here are both variables or factors. So we add this one here. And then we just do exactly what you expect with the edges. We basically we remove all the edges that related to these old factors because they're not in our network anymore. And we add an edge between every variable in x tilde and f tilde. Because again, f tilde is a function over these variables. So there has to be an edge between all the variables in x tilde and f tilde. So it looks a little complicated, but it's really actually conceptually incredibly simple. Take everything that involves xi, multiply it together, sum out xi, and put it back in the network. So in our example, let's say we have this is a Bayes net, remember. This is a factor graph representation of our Bayesian network. We want to eliminate, say, x3 here. That's a bad idea, by the way. Don't eliminate x3 first if you were actually going to do this. That would be a horrible idea. But let's do it. So here we want to eliminate x3. So our factors involved are f3, f4, and f5. Those are the ones connected to it. The variables they involve, which is our x tilde, are all of them in this case, x1, x2, x4, and x5. This should be x5 here. Sorry. And now we do everything else, right? We multiply those together, create our new factor f tilde, which is a function of, oh man, this should be x4. Throwing out typos all over the place. This should be, so x1, x2, x4, and x5, which is just going to be take all these factors that involve f3, sorry, all the factors that involve x3, these ones, multiply them together, and then sum out x3. What we are left with, then, is a factor graph that looks like this. We no longer have the variable x3 in it. We've eliminated that. And instead, we have a new factor that ties together all these variables. Now, to do sort of full variable elimination, what we usually mean when they say variable elimination, is just the repeated invocation of that procedure. If you want to say, compute P of f subscript I, or some subset I, you just take every variable that is not in xi and eliminate it. What you're left with is a factor graph that represents this thing exactly. Okay? Similarly, if you go one step beyond and actually eliminate all your variables, what you're left with is actually no longer a function, it is a constant. And that constant for a general factor graph will be equal to the partition function. So if you want to compute the partition function, you just eliminate all the variables. That will give you a constant term, not a function anymore, but a constant term that's equal to z. Remember, because z is the sum over all possible x of the unnormalized probability. So you eliminate all of them, you'll get this. Now, the factor graphs you get here are still not normalized, I should add. So if you want to normalize them, you have to either at some point just compute the partition for an individual one here, or finally compute the final partition function too. But they are still valid factor graphs that represent those distributions over the subset of variables you have not eliminated. And one final point here, maybe not final, but one point here that's very important, is that the ordering you do this matters a lot. So I gave this example before, saying it was a really bad thing to do in this case. And you can kind of imagine why, right? Because we've created a factor that involves all our variables. And in fact, this term right here was a factor, a product of factors, which is really just, again, one factor. This is a table of values. And this term here involved all the variables. So we've gone and just enumerated all something that is of size 2 to the n. So we have lost all advantage of having this compact representation, at least from the inference side of things. We've done all the work that we would have to do just by enumerating it all anyway. What we should do instead, of course, is eliminate these in a different order. So say I wanted to compute P of x4. That's this guy down here. What I should do is something like this. Take x1 first, eliminate that. We're left with this new factor. Then x2, now we're left with this factor. Then x3, now we're left with this factor. Then x5 and that factor. Now we just have a factor on x4, and that just is the probability of x4. You might have to normalize it, but that is the probability of x4. So the ordering matters a lot. And a good ordering can give you the benefit of this nice compact representation, whereas a bad ordering can give you a very bad breakdown here. Now, one fact which gets to a question someone asked before is that for certain structures like chains or trees, you can always come up with a good ordering. Basically, you do the leaves first, is the basic idea. Always do the edges. That will always be a good ordering. Unfortunately, you can't always do it so easily. So there's this property of the graphical model called the tree width. And the tree width, kind of informally, it's not. Sometimes you'll subtract up a constant here, but basically it's the size of the biggest factor that you form when you do variable elimination. Maybe minus the size of the biggest factor in the initial tree, but don't worry about that. So that's the tree width of this graphical model. And as you might imagine, essentially tree width is the size of the biggest factor. So by definition, because we're forming it, we know that inference is going to be exponential, right? Have exponential complexity, both in terms of memory and time, in the tree width of that graphical model. Now, unfortunately, and tree width usually is defined as the size of the maximum factor using the best possible ordering. So I'm going to use the best ordering I can, and what's that tree width? Unfortunately, again, so it's already bad because we're already exponential in it. Secondly, we can't even find the best variable elimination ordering. Even that problem, finding the best one is NP hard, it turns out. So that's too bad. And even worse, maybe, is that some very simple graphs, we actually do know they have tree width, and unfortunately it's very big. So for example, this graph, which is very common in things like image processing, this is a grid Markov random field. This graph here, the tree width of this graph is just equal to the maximum dimension, the minimum dimension on either axis. So if it's m by n, the grid size, it's the minimum of m or n. Which if you have, a 200 by 200 image, and just two values, you're still 2 to the 200. And 200 is not very big for an image. So lots of downsides here, right? It's exponential in this tree width. Oh, by the way, we can't always compute the tree width. And by the way, when we know the tree width, it's sometimes pretty bad. So this is sort of an interesting point here, because this graphical model is still very compact in terms of representing the distribution, right? We need many fewer parameters here than we were. I mean, we just need one for each edge, 4 numbers for each edge and 1 number for each node for a Markov random field like that. That's much less than 2 to the n. But if we want to actually, I guess 2 here to the 2 to the m times n. But if we want to do inference here, we can't really exploit that whole benefit. We're not quite 2 to the m times n, but we're still 2 to the m, to the minimum of m or n, which can still just be too big. So inference methods, kind of at their core, they try to exploit this graph structure, but you can't always do it as much as you would like. You can't always get a representation for inference that is as compact as your actual graphical model representation. A couple final points here, and I don't think I'm going to get through approximate inference. We can either just leave that for the ether, and you can read the notes for it, or we'll do it next time. But some extensions to this. It turns out that the one kind of annoying thing about this algorithm here is that you have to rerun it every time, right? Every time you want to issue a new query, you have to rerun your whole variable elimination and eliminate new variables. That seems like a lot of sort of repeated work, right? And it is. What you could actually do instead is a slight extension of this method. You could actually sort of do the same kind of construction of intermediate factors only once for the whole network. You actually do 2 passes. You do kind of a forward pass and a backward pass, they're called. And don't worry about the details here. They're a little bit complex, but not conceptually very hard at all. You're basically forming factors in one direction and doing it in another direction. And if you do that, then you can actually answer all inference questions, or all sort of reasonably sized inference questions. By reasonable size, that just means, if you're asking an inference problem still over an exponential number or over a large number of variables, you still have to enumerate a lot of things. But if you ask sort of a small size inference question, you can answer that without doing another whole variable elimination procedure. You just actually sort of form directly from your intermediate factors in your forward and backward pass. This is called in general the junction tree or the clique tree algorithm. Clique tree, I guess. And you probably, if you see sort of a description of this in a book, it will probably actually be this algorithm, not just simple variable elimination. You will also probably see weird notation like this, where people say things like mu of x to z and stuff like this of things I don't even know, mu xi, xj of xi, stuff like this. You'll see these things in books, and they're essentially exactly the same. These mu's here, which they call messages, are just the intermediate factors you form in variable elimination. It's a little bit nice to think of these things as actual kind of messages that different nodes are sending to each other. And that is why people use this notation. I think it's not the best for sort of introductory lecture, but this is what you will see if you read a textbook on this. You will see these muse, these messages, these things like this. Just be aware these are just the reduced factors you're forming during variable elimination. Finally, one last thing. How does this all relate to map inference? Well, map inference, remember, is asking the question of not just what's the probability, but what's the most likely assignment of variables. It turns out you can use almost the exact same algorithm to answer this question as well. The only difference is, instead of this equation here, where you take a sum and a product, the sum of a product, rather, you still form the product of all your factors, but then you take the maximum over the xi. This is the variable you're eliminating, instead of the sum over xi. And if you do this procedure, you will, instead of summing out xi, you will take the max over xi. And so that will eliminate, that will essentially give you a maximum, it will give you the map solution to these things. Now, if you don't just want the maximum probability itself, that's what you need to do to compute the actual maximum probability. If you also want the assignment to variables that maximize that probability, you have to keep track of one more thing. You have to keep track of what actually is the xi for each setting of the other values here. What is the xi that actually maximizes that thing? So you basically have to keep track of one more function, which tells you for any assignment here what is the maximal xi. So kind of the argmax as well as the max of that. But that's it. That's all you have to do. And that will give you then the same algorithm, all the same sort of sets we decided before, et cetera. That will give you the map solution. OK, I think we'll probably just jump to the next stuff next time. So I just want to give a quick 4-minute rundown of approximate inference. You can read the slides. They'll hopefully somewhat explanatory later, but I'll just give the 2-minute summary here. 2-minute summary is oftentimes, so we have these situations here, right, where there are graphs, unfortunately, that we cannot solve, right? The graphs themselves are kind of compact, yet we can't actually perform inference in these things. What do we do in that case? There's a couple things you can do. A very common thing to do is to, rather than trying to actually compute exact probabilities, we just try to draw samples from this distribution. Right, so we just try to sort of essentially get some samples from it, and that oftentimes is almost as good, or as good, as being able to compute exact probabilities. Or we sometimes want to do this just for its own sake, just draw samples from a distribution. That can be very helpful. For things like Bayes nets, you can do that kind of immediately, right? At least if you wanted to assign a full set of variables, you just sort of follow the order of the Bayesian network and generate things according to their parents. That's easy. For Markov random fields and factor graphs that are not normalized, it can be a lot harder. You have to, normalize them first, which is as hard as inference is. So we're not really getting anywhere. And because of that, there's a very common technique people use called Gibbs sampling. Gibbs sampling is kind of an incremental way of sampling from the true distribution of your graphical model, but doing it in a way where every step remains tractable. Essentially, all it is you iterate a bunch of times, you pick some random xi, and then you sample xi from the probability of xi given the current value of all other variables in the network. And by the way, because of the factor graph property, this would be just the ones that that border on just the factors that sort of are connected to that variable there, or the ones you have to multiply together. So this is a much smaller set here. You can normalize that one, draw samples from that one, and then use that to sample xi. And you draw some other random xi, sample that one, given all its neighbors, set the new value of that. And you just repeat that process. And it turns out that actually will converge to the true samples from the true distribution. Of course, these are, again, as I said, sort of NP-hard problems to solve in general. So the caveat is that it may not converge to the true distribution for an exponential amount of time. That is a big caveat. But at least conceptually, it's a very simple procedure that can work very well in a lot of cases. And it's a subset of a much more general class of methods called Markov chain Monte Carlo methods. Finally, the last thing I'll say is that you can also formulate, turns out, you can formulate problems in inference as optimization problems. And sometimes things that happen there that are very, very cool. So for example, you can think of the problem of maximizing over x the probability of x. And while I have the details in the next few slides, as you may imagine, you can actually set this up as an integer program, right? Because basically, the variables here, they're integer valued. You might imagine, as you would sort of think, you can set this up as an integer program, the problem of finding the x that maximizes this probability here. OK? So what's really cool about that, I'll just say one thing. That becomes an integer program. Here it is. Don't worry about what these actually are. But if you run the integer program on this grid network with certain weights here, this is the grid network you can't run actual inference on. If you run this integer program formulation, and remember, integer programs are nasty. You all solved them. You all saw how nasty they were in the last homework, right? But the ones we like are the ones where you just branch and bound terminates immediately, because the LP solution actually gives you the actual solution. This thing has an integral solution, and it's just there. It turns out this setting here, with certain weights that meet certain conditions, will give you an integer solution for the LP relaxation. So for images, for example, you can compute the map solution for these things that have a tree width of hundreds using optimization methods. That's very cool. That's all we'll say for today. There are questions you can tap me afterwards because we're over time. But next time we'll start talking about the dynamic version of this, where you actually have to now just not make inferences, but also make decisions under uncertainty. OK?